All right, recording, rolling, and let's start this thing. When a car's speed triples its kinetic energy, increases 9 times because 1/2 mv squared. That speed's getting squared. A factor of 3 squared, 9 times. Right. That would, of course, translate to 9 times the braking distance if it stops. Right. All simple machines ideally work on the principle that oh, nice. Right. Because all four of those statements are true statements in isolation, but the one that actually applies to simple machines is, yeah, this right here. Work input equals work output. When you guys rigged up those pulley systems, you had force times distance in equals force times distance out. Right? You could get a mechanical advantage from that, but the amount of energy is constant. I got Addie, Max, Steven, Sydney, and Catherine. How many joules of work on a box? 25 newtons for 3 meters. Work equals force times distance. 25 times 3, 75. 75 joules. Right? Force dot distance. How much power? 40 joules of work in 5 seconds. Eight watts. They got power is work per time. Energy transfer per time. 40 joules divided by 5 seconds. 8 watts. We got Sydney, Addie, Steven, Max, Catherine, keeping that lead. Where does a satellite in elliptical orbit have the greatest kinetic energy? Oh, nice. All right, yeah, the point closest to the planet. Here, I'm gonna flip my screen just because some of my other classmates kind of struggling with that question. Not you guys so much, but here we go. Here could be maybe a satellite in an elliptical orbit. No, the total mechanical energy is conserved, right? Which means far away is a lot of potential small kinetic, and close is small potential large kinetic. So like speed up, it'll speed around really fast, and it's kind of slow over here. All right, there you go. Right, so back to computer screen. How are we doing on points? We got Sydney, Max, Steven, Addie, Catherine. What remains constant for a satellite in elliptical orbit? Yeah, the total mechanical energy, right? Which is the sum of potential and kinetic energy. I should say too, if you apply potential energy to this, you want to use not the mgh because that lower g would not be constant, but the negative g mm on r version, right? Interestingly, if you add potential plus kinetic from that universal point of view, it always comes out to be a negative number of joules, kind of weird concept. I don't think that'll show up on the AP exam, but just in case, right? At least you'll introduce that idea. Oh, Smingus topping in the top 5. Catherine on fire. Machine puts out 100 watts of power for every 1,000 watts input. What's the efficiency? %. There you go. Right, 100 watts over 1,000 watts, right? Now the other 900 watts maybe is dissipated through possibly like thermal, maybe something like that. If you run your car and then feel the engine, it like heats up, which didn't make the car go forward, but it's like waste heat. All right, points. Potential energy is the energy an object has because of its location, height. So MGH. So it's actually 3 things, right? Mass, gravity field, height, MGH. Right, put it all together. Yeah. So position, height. All right, more points. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is the same force. Is that Newton's third law of motion? Newton's third law, same force, right? There's like an explosion in the barrel of the launcher. Yeah, same force on the ball back on the launcher. Same force. Right. That's really a setup for this next question. Double. Table tennis ball launcher is fired. Compared to the impulse on the ball, the impulse on the launcher is also the same. Okay, so we're getting into the momentum questions, right? Like on your review, we're in the momentum section. So what is impulse? Impulse is a transfer of momentum. And there's a couple perspectives on that. You could do mass times change in velocity, but that comes from applying a force for a time interval. Well, the last question was the same force, right? Same force on the ball as on the launcher, but it's also for the same amount of time. Maybe it's like a fraction of a second, right? So force times time forward on the ball equals force times time backward on the launcher. It's the same impulse, right? One positive, one negative, but the same magnitude. All right. That's Stephen, Addie, Stephen, Max, Catherine. Momentum of an object defined as the object's mass times velocity. Momentum is mass times velocity. You guys remember that's a vector value, so forward versus backwards matters. It's conserved in collisions. Whenever you see collision, think something to do with mass times velocity. Smingus is back in. Addie, Stephen, Max, Catherine. Velocity of a moving object doubles. What else also doubles? Momentum. Momentum mass times velocity. Double velocity, double the momentum. Right, guys. If you double the speed, what happens to kinetic energy? Goes up by a factor of 4, right? Because factor 2 squared. Right. Acceleration is a rate change of velocity, so it doesn't quite match up. All right. Ooh, 12 in a row. Catherine has. Ooh, Catherine's got a perfect game going. We don't jinx it there. Cannon recoils from launching a cannonball. Speed of the cannon's recoil is small because yeah, cannon has so much more mass, right? So identical force on cannonball as the cannon, identical amount of impulse, yeah, but more mass is less change in velocity. There you go. All right, points. Oh man, it is a tight points race. Oh no! Help you guys out here. Right, a piece of putty with 5 units of momentum collides and sticks to a bowling ball initially pressed. Now both roll off together with a combined momentum. The putty comes in with 5 units of momentum, collides and sticks. They both roll off together with a combined momentum of also 5 units. Okay, right? Because if the bowling ball is at rest, there's no momentum there. Right, here comes the putty with 5 units, collide and stick. Now momentum's conserved, right? Right. That's a perfectly inelastic collision. Right. Momentum is conserved. 5 units equals 5 units. Right, like kilogram meter per second. A bouncy ball coming in with 5 units of momentum. The bounce off a bowling ball initially at rest. Now the bowling ball itself is set off into motion with how many units of momentum? That's the bottom picture. The bouncy ball point. Yeah, more than 5 units. Okay, so for example, here comes the bouncy ball with 5 units of momentum, maybe 5 kilogram meter per second, and it rebounds, let's say, with like 3 kilogram meter per second relative to like a tree in the background, right? So, guys, what is the difference between +5 and -3? 8. 8. So the impulse on the bouncy ball was like 8 units of momentum. Therefore, that's what was transferred to the bowling ball, right? Now that is a weird outcome. So the other thing you'd want to keep track of is kinetic energy. Guys, can kinetic energy increase during a collision? No, at best it could stay the same. It'll probably go down a little bit. Okay, so yeah, that's kind of weird one, but kind of fun weird corner. 2 kilogram ball, 3 meter per second. What's the momentum? Mass times velocity. Hey, everybody getting points. Everybody gets the physics points. Ooh, Steven, Ade, Steven, Max, Catherine. Collision is elastic if all right. So here, the sort of like textbook definition of elastic I told you is, well, not only is momentum conserved, which is true for all collisions, right? But kinetic energy is also conserved. That's elastic, right? That's like here, the Newton's greater right here. It's probably pretty close to that. Right? Now, kinetic energy is conserved. Okay, so the objects don't stick together, obviously. So that is true, right? That would be inelastic if they did. But also, if kinetic energy is conserved, that means that there was no force times distance that went into deforming the objects, right? And also that there's no energy that escapes to like a thermal energy loss, right? Yeah, so all the statements are true. They will all correspond to elastic. Force of an apple hitting the ground depends upon. Yeah, all those factors, right? The faster it hits, the more force. How about this blue and this yellow? Guys, suppose the apple hits a mattress and then that extends the time interval. Would that be a relatively smaller force? Versus if it hits a bam, concrete ground, that collision happens in a tiny time interval. Is that a larger force? So force times time interval, right? Decrease the time interval, increase the force kind of thing. How about if the apple bounces? Ooh, that kind of reminds me of the putty versus the bounce ball off the bowling ball, right? Guys, what's more force? Sticking or boing bouncing? What's more force transfer? Bounce, yeah. The bounce is corresponds with more force, right? Up to twice the force. It's elastic versus inelastic. All right. Two gliders, same mass, same speed, move toward each other on an air track and stick together. What's the post-collision speed? Yeah, 0, right? So like 9 units momentum to the left, 9 units momentum to the right, zero's out. Boom. 0. You got vector quantities, negative and positive, cancel out. Which has greater linear speed, a horse near the outside or inside of a merry-go-round? Oh, yeah. All right. Students been struggling with that one all day today. So here, for the video for sure, I'm gonna show you guys here. So, oh, here's our turntable. Or hey, could this be a merry-go-round? We're up in a helicopter looking straight down. See that? Hey, see these 3 horses? So give this thing a spin. Now, remember, there's 2 kinds of speed. We got linear speed in meters per second. We got angular speed in radians per second. Guys, do all these 3 horses have the same turns per time? Yeah, they all have the same angular speed, right? They all make the same revolution at the same time, right? But multiply by their distance from the center, and you get how fast they go relative to the outside world. Like this horse in the middle, he's just getting dizzy, but he's not really moving anywhere with any linear speed. If this guy out here points a radar gun at him, he reaches 0 meters per second, and his spin rate times 0, 0. Right? And then, guys, if this horse is going 7 meters per second, how fast is this horse going? 14 meters per second, because he's twice as far out. That's a direct relationship right there. Back to Kahoot. Back to the horses. I got Sminga, Steven, Ade, Max, Catherine. Which has greater angular speed, force near the outside or inside of a merry-go-round? Yeah, same angular speed, same turns per time, same radians per second. There you go. There you go. All points. If you whirl tin can into a string and the string suddenly breaks, the can will. The colors match. Which color? Yeah, there you go. Fly off tangent to its circular path. Of course, I stole that graphic from the gravitational version of that question, which had the same answer. Yeah. Fly off tangent to its path. That's law of inertia, isn't it? That's the first law of motion right there. Centrifugal forces, in quotation marks, are an apparent reality to observers in a reference frame that is. Yeah, rotating is what I'm looking for. Because if you're on the merry-go-round, let's say you're blindfolded, it feels like you're being thrown towards the outside, right? Now that's really kind of a more complex story, right? It's actually, well, you're actually trying to move in a straight line, law of inertia. There's some forces actually pulling you in, right? Called centripetal, right? Centrifugal means center fleeing. Notice it's in quotation marks. Guys, on the AP exam for like FRQs, when you're writing out paragraphs, are you ever going to write that phrase, centrifugal? No. And then because AP approaches all problems from an inertial frame of reference. You guys see that green one says inertial frame, right? What does that mean? That means you're non-accelerating. So if there's someone on the outside who's watching this whole thing rotate, maybe we're up in the helicopter looking straight down, right? We've got an outsider's perspective, right? Maybe we're at rest. That could be inertial frame of reference. But remember, that's physically indistinguishable from moving at constant velocity. Remember how you can never feel the speed of a car, right? So this red, this blue, and this green all kind of go hand in hand, right? But if you're on the platform that's rotating, it feels like you're thrown towards the outside of the platform. Okay, that's that center fleeing apparent force, right? All right, there you go. Elias, Mingus, Ade, Max, Catherine. As the rotational speed of a space habitat increases, the apparent weight of everybody inside. Hey, spin it faster. Everybody feels heavier. There you go. There you go. Right. So the centripetal acceleration, see like the artificial gravity field, you can think, right? Omega squared times r. Guys, what if you spin that O'Neill cylinder 3 times the angular speed? Guys, you speed up 3 times. How many times heavier is everybody? 9 times as heavy. Because omega squared times r, right? 3 times the angular speed is 9 times as heavy. All right. Car travels in a circle at constant speed. The net force on the car, it's on a curved path. Yeah, there you go. Directed toward the center of the circle, some kind of centripetal force. Maybe it's provided by friction if it's a flat road. Maybe it's the horizontal component of normal force if it's on a banked road. Yeah, right. No, there's no forward force because of the constant speed. So the fact that the speedometer reading is staying the same, right? I mean, there could be that too if the car was speeding up or something, right? Or hitting the brake. Yeah, right. So the fact that it's on a curved path, the answer could never be the right answer. Right? Yeah. So there's definitely some kind of centripetal force going on for sure. Wrench slid spinning over a frictionless tabletop. Its center of gravity follows. So the center of gravity follows a regular straight line path. There you go. Like if you attach some LED lights to the wrench, right, one of those lights would follow a straight line path. The one at the center of mass. There you go. Yeah. Which of the following is the center of gravity located at a point where there is no mass? D for donut. Center of mass, donut. If you did that whole thing, or you hang a donut from a string, right, it would always go through the donut hole. Donut. Object will fall over if its center of gravity is. Yeah, there you go. Not over its area of support. When you're walking around, your area of support is like the soles of your shoes. Did I tell you guys if you put your back against the wall, put your heels against the wall, reach over, try to touch your toes? Really hard to do because your center of gravity, if it is not over, well, your feet, then it'll topple over. Oh. Eli, Addie, Steven, Max, Catherine is back on fire with 14 in a row. Ooh. Object thrown in the air with the spin rotates about its. Center of gravity, yeah. Which could be geometric center or midpoint if it's like uniform, but yeah, center of gravity is the universally true answer. There you go, center of gravity, center mass. Picture hangs on a wall from a wire passed over a supporting nail. The picture is in stable equilibrium because. Yeah, okay, so those are all true statements, right? Center of gravity is directly below the supporting nail, right? Just like you guys do with the foam boards and the string. Any slight push would raise its center of gravity, which it doesn't want to do. And then after that small push, it returns to its original position. Yeah, those all align to it being already in stable equilibrium. There's a picture hanging on the wall. There's a small earthquake comes along. Picture just settles back into its original location. Torque. R cross F, right? R cross F. There you go. R cross F. Turn a wrench. About a nut. Right? The longer the. Try loosening a nut with a wrench. The nut doesn't give it all. You increase your chance of success if you. There you go. All the above. Yeah. So R cross F. Extend the lever arm. There's your R. Push perpendicular. There's, well, the cross product. It's like 90 degrees. And there's your F. Exert a larger force. All the above. R cross F. There you go. The resistance an object has to change in rotational state of motion is called rotational. Inertia, rotational inertia. There you go. Right. The last lab we did, or how about that meter stick with the weights taped to it too, right? Try to shake that back and forth. Rotational inertia, resistance to change in rotational state of motion. Huge rotating cloud of particles in space gravitates together. As the cloud shrinks in size, it rotates. Yeah, faster. Right? That reminds me of the ice skater question. There's conservation of angular momentum, I times omega. So if I decreases, omega increases. There you go. There you go. When an ice skater pulls his hands in to turn faster. Yeah, so all the statements are true, right? So the guiding principle is this gold one here. Angular momentum is conserved. That's capital L, right? Well, what is capital L angular momentum? Well, that's I times omega. So as your rotational inertia decreases, that's pulling your hands in, right? Then your angular speed, omega, is going to increase. Right? So yeah, so all those go hand in hand. All the above. I got Mingus, Addie, Steven, Max, Catherine going in for the win. Sydney's back. For the win! A ring and a disc roll down a hill. Which way reaches the ground first? Reaches the bottom first. The disc, right? Because the ring, the mass is distributed all towards the outside, has a lot of rotational inertia, say like per unit mass. Right? The disc, mass distributed closer in. Hang on a minute, maybe I left off some information. Guys, what if you have different size rings and discs? What different masses, different radial size? Does any of that matter? It all cancels out. Right? Guys, see the poster up there, the basketball rolling down the incline? Mass and radial size shows up at some point, but it cancels out by the end. Right? So if you have lots of rings and lots of discs rolling down hills, all the discs will beat all the rings. What if the mass is uneven? Well, okay, that might be. Steven, Max, and the gold. Catherine. Yeah, runners up. Hey, and Sumingus. Nice job. Nice job. All right, let's flip over to these posters.